Again, my name is Will Jacobs with Stan Lindsay out of Atlanta. And today we are going to be talking about erection engineering basics. And before we get into the basics of erection engineering, the first thing that we're going to talk about is exactly what erection engineering is. We need to have a definition for it before we dive into the basics behind it. After that, I'm going to talk about where these requirements are coming from to begin with, like who's telling you need to have an engineered erection plan, what industry standards there are out there. We're going to talk a lot about wind loading. That's one of the key issues affecting this segment of the industry. Then we'll go over some challenges and solutions for different aspects of erection engineering. We'll walk through the anatomy of an engineered erection plan, so the pieces and parts of what I would consider to be a fully thought out erection engineering plan. And for fabricators and erectors, we'll go through a couple of items about how you can sort of plan for and minimize the impacts of this kind of planning as you go about bidding a job. And then finally, if we have any time left, we'll take questions. So in terms of a definition, this is my personal definition. So erection engineering is engineering associated with the development of an erection sequence in collaboration with the fabricator and erector that is structurally stable under all applicable temporary loading at each stage of construction, including the effective communication of this information to the fabricator, erector, and general contractor. And so what that normally consists of is things like the design of temporary bracing and shoring elements, the review of and modifications to the permanent structural system as necessary to support temporary forces, reviewing connection design forces and creating alternate force flows or upgrading the connections if necessary. And then there's a whole other subset of erection engineering for logistics, crane planning, truss racks, things like that. We aren't really going to get into that side of things today. We're going to focus on more of the engineering aspects. But I want to jump back and focus on two things with this definition. That is collaboration and communication. The key to being a successful erection engineer is communication. Because you have to be able to talk to and deal with not only the people in the office, but all the way down to the boots on the ground, right? The guys that are implementing your plan, the guys that are actually rigging the trusses, those are the ones that make it a success. And this is difficult for two reasons. First of all, communication is not really a structural engineer's forte. Certainly hasn't been mine. It's a little bit difficult to get out there and talk to these guys day in and day out. And secondly, a lot of the people that you're talking to don't want to listen to you. An ironworker texted this to me the other day, and I think this sums it up. Ironworker, using common sense and a torch to fix what your computer messed up. So a lot of the guys think of the engineer as sort of the enemy, right? Those are the guys that are making their life more difficult, and it really should be the opposite, right? We should be the ones that are working with them to develop solutions to make things easier. And what I found is if you go out in the field and you talk to the guys and you spend more time listening than talking, you listen to their ideas, you listen to the way that they want to build it, and then you take that and you put some numbers to it and do your best, they will be a lot more apt to follow the plan than if you just shove an erection engineering plan down your throat. So the key to all of this is listening. As an aside, my wife said the same theory applies to marriage. I remain skeptical. So, where are these requirements coming from? Generally drawings, right? So you have a structural drawing and they all have some note like this that says the structure is stable only in its completed form, as if the structure just appears out of thin air and gravity turns on. And we all know that that doesn't happen and it needs to get from point A to point B. So where in the building code does it tell you who's in charge of getting from point A to point B? Well, we'll start with the building code, IBC 2018. I think it's up to 2,000 plus pages, and it has really one sentence that's applicable, and it says that design, fabrication, and erection of structural steel basically should be in accordance with AIC 360. Okay, thank you, IBC. Move on. AIC 15th edition manual, nice new blue manual, contains the specification and the code of standard practice, right? So now we're getting somewhere. Let's take a look and see what the spec says. So in section M4.2, it says that the structure shall be secured, in highlight here, to support dead, erection, and other loads, such as construction wind loading, anticipated to occur during the period of erection, and that temporary bracing shall be provided in accordance with the requirements of the Code of Standard Practice. Okay, so let's dig down a little deeper. The Code of Standard Practice, section 7.10.3, says that it is the erector who shall determine, furnish, and install all temporary supports, yada, yada, yada. All right. Notice it doesn't say the erector shall hire an erection engineer to produce a signed and sealed erection plan. It says the erector shall determine. Right? So it's sort of left in the eye of the beholder what determination is required. There's a lot of guys that have been doing this for a long time, and not every strip mall out there needs a signed and sealed erection engineering plan. Right? But as some of these buildings get more complicated, more difficult, oddball framing, long span trusses, things like that, even metal buildings are quite stability sensitive. It's a good idea to get an erection engineer involved. Now that's the requirement. A lot of times you'll have an EOR specify you need to have a signed and sealed erection engineering plan. This is just one example I grabbed from a project, and you can see highlighted here, this is from the main specs, and it says, for all loads in the Code of Standard Practice in ASC 37, you shall have a qualified licensed professional engineer hired by the erector to design the temporary bracing. So that is where really a key requirement requiring a structural engineered erection plan comes in. So what industry standards are out there? Probably the primary one is ASE 37. This is the sort of gold standard for loading on structures during construction. I'm on this committee. It recently had an update in 3714, and we're already on the way to producing the next update. Second would be AIC Design Guide 10. This is a lovely document that is also moving toward an update, my understanding toward the end of the year, that goes through a lot of the issues associated with low-rise steel building erection. And then you get into ASME documents. There's a lot of these, and they're all very useful. BTH probably is the most useful. This is the design of below-the-hook lifting devices, lifting lugs, spreader beams, things of that nature. And then there's a whole series of B30 documents that go into different types of cranes, crawler cranes, tower cranes, things of that nature that you'll need to be familiar with. And more recently, if you get into a lot of crane planning, there's a document called P30.1 that is the planning for load handling activities. And this document goes through critical lift planning and what you need to have on your drawings for that kind of activity. You're going to learn a lot more about wire ropes than you ever thought you would if you're in this business. So the wire rope user manual is a good start. And then there's a whole bunch of manufacturers' catalogs, Surtex catalogs, things like that for you to learn about shackles and turnbuckles and chain falls and all the various sundry lifting aids. And finally, I was made aware recently, that being this morning, that the Metal Building Contractors and Erectors Association is going to have a design guide specifically for the stability of metal buildings coming out toward the end of this year. So that's all the guidance. Really all of the requirements are in OSHA, and these are sort of mandatory, but other than that, not very helpful. You have to do these couple of things, but them in of themselves will not produce a stable building. 4 bolts with a column, no double connections, minimum of 300 pounds at 18 inches from the face, things like that. So those are sort of just your minimum OSHA compliance requirements. But the biggie comes in construction wind loading. So really you've stepped into what's going to be a presentation on wind loading that happens to have a little bit of steel in it, because for the next 20 or 30 minutes we're going to talk about construction wind loading. And you've already got your PDH, so if that sort of thing doesn't appeal to you, now's your chance. All right, here we go. I warned you. Wind speeds. For a permanent structure, the gold standard for wind loading is ASE 710, 716, whatever is in force. And as we talked about for temporary construction, we're talking about ASE 37. Right? That's its companion document. So if we take a look at a typical inland location for ASE 716, you're required to design the permanent building for 115 miles an hour. Right? If we look at Atlantic City, which is not far from here, you're going to be at 127 miles an hour. Right? It's close to the coastal zone where it can be affected by a hurricane. So that's for permanent structures. What about for during construction? Right? If you look in ASE 37, what they do is they have a list of reduction factors that you can use for different construction periods. So if you can build your building in less than 6 weeks, you can reduce those permanent building wind speeds by 25%, by a factor of 0.75, and so on and so forth, depending on how long your construction period is. Right? That's for an inland job. For a job on the coast in a hurricane-prone area, so for example, Atlantic City, if you're outside of hurricane season, so if you're erecting outside of hurricane season, you can use the reduction, just like you were inland, of 115 miles an hour. So for 6 weeks to 1 year, you can reduce the wind speed by 20% and design all of the temporary bracing for that lower wind speed. If, however, the building is being erected during hurricane season, according to ASC 37, you are not allowed to use that reduction, right? So you would have to use the full 115 miles an hour. And you also have to have the ability to resist a hurricane within a reasonable amount of time, which is sort of left ambiguous. But if you think about the prediction capabilities for hurricanes, you've probably got 2 or 3 days max to be able to move the bracing from a level of 115 miles an hour up to a hurricane. Now, I personally think that it makes no sense that you can't use the reduction if you already have a plan in place for the full hurricane wind loading. So I'm not telling you to do that. I'm just telling you I do that. There's the other aspects of what about during the day? This continually monitored work period is the way they refer to it. So that's if you stand your column and you let it go. If you set a truss and you let it go, what do you have to design it for? Do you have to design it for the full 0.8 of 115? And the answer is no. You're allowed to design it for less. And again, that's sort of left up to the eye of the beholder. We generally set it to a reported wind speed of around 30 miles an hour, right? So that's around the range where most of your cranes would shut down. And that reported speed is the speed you would see on your cell phone app, right? That's if you look up weather.com and it says 30 miles an hour, because the guy in the field doesn't have a 3-second gust phone. He has a weather app phone. And so if you take that 30 miles an hour and you convert it to 3-second gust ultimate, your design wind speed for a daily wind is around 45 or so miles an hour. Keep in mind that pressure is a function of velocity squared. So when we're changing these velocity numbers, it's got a much larger effect than that on the force. So for a 50 mile an hour wind, you've got a certain pressure. For a 72 mile an hour wind, you would have almost twice as much, right? So even though your velocity only changed by 20 or 30%, you've got a 70% change in force. It's just something I wanted to keep in mind. So how does all this actually work out for a real building? So let's take a look at this. This is sort of an example here, but you'll get the point. The velocity for this building is Atlantic City, 127 miles an hour. And we'll just say that the pressure works out for that miles an hour to be 20 PSF. During construction, outside of hurricane season, if I can throw this up in 6 weeks or less, I get to use a 25% reduction, so 95 miles an hour, which works out to be a pressure of 11.5 PSF. So, ooh, great, you know, that's almost half. This should be no problem. But unfortunately, that's not exactly how wind works. So if you look at the building on the screen, you'll see that it has all of the walls around it. And if you think about wind as a fluid, which it does happen to be, what's going to happen is it's sort of like the rock in this picture. The wind is going to flow down, it's going to hit the rock, and it's going to go around it, and it's going to keep going. So in the permanent building, where you have walls on it, you get pressure on the front, and then it goes all the way around it, and then you get a zone of suction on the back. The temporary condition is sort of like a series of logs. If you have a log on this picture, you've got the wind that hits that log, goes up and over it, and then hits the next log, and the next log, and the next log, and the next log, right? So your wind force looks more like that. You have a negative pressure zone on the back of each one of these members. And that, in more engineering-y terms than logs, is a drag factor. It's generally around 1.8 to 2 for a standard beam. So if you look at what that works out to, we cut our pressure in half by the wind load, and then we just doubled it back, right? So now we're right where we started, more or less. But there is this concept of shielding. And what happens there is if you get the beams close enough, you start to see less of an effect. You don't have room for the wind load to speed up. And if you get close enough together, they act as a single unit. So shielding is handled in ASC 37 very conservatively. They say that the loads on the first 3 rows of elements are not reduced at all, and then fourth and subsequent, you get a massive reduction of 15%. Right? So it really doesn't do a lot. So if we take that 15%, we get to reduce our 23 PSF down to 20 PSF. So we're exactly the same as we were when we started the design of the permanent building, even with all of our reductions. So then it comes out down to just area, right? So when I have a projected area of this building, in the permanent condition, I have a wall. So I got 20 PSF, it hits that wall. That works out to be a total shear of 31,000 pounds for this made-up case. But in the temporary condition, if I don't have any walls, the area that I'm hitting is each one of these beams, right? So let's just take these beams and start stacking them, because that's really what the wind is seeing. So that's the wall that the wind is hitting. So you have the same amount of PSF hitting twice the effective area. So your wind shear in the temporary condition, in this particular case, is double. And this happens a lot. There are a lot of buildings where you end up with higher wind shears in the temporary open cladding case, no cladding case than you do in the final permanent building case. And this is in the non-hurricane area, right? If you actually had a hurricane where you didn't have any reductions allowed, now your wind shear is 4 times that of the permanent building for the temporary wind load case. So what happens? Generally nothing, because a lot of times it doesn't see that kind of load. Occasionally this, which is what you're trying to prevent. This was in Texas, 2011, and OSHA actually cited a lack of planning per ASC 37. So those guys are aware of this. So let's sort of talk about some challenges and solutions associated with these issues. And we'll start with wind loading, right? That was sort of the big challenge we went through. So what can we do about it? One of the things is to look at alternate shielding models, right? I mentioned the ASC 37 was quite conservative. Quick refresher, no reduction on the first 3 rows, and then a reduction of 15%. Right? There's a lot of other less conservative sources out there that you can look at. Here's a listing of a few. ASCE's Design Guide 10, which uses a German document as a basis. You got ASCE's wind load on petrochemical facilities. Wilford and Alsup has a British document. European Material Handling Federation, FAM 1001, has some good rules on this. The National Building Code of Canada, Australian New Zealand standard, that should say, Cranes and Derricks 4th edition. Basically everybody but the United States has reasonable reduction values that you can look at. And that's something ASC 37 certainly has on our radar moving forward. And all of these methods are similar in that you have some sort of a table like this where you have a certain porosity or solidity of the members. So say you have a wide flange beam where the wind load just hits it, or you have a joist where the percentage of solidity is more like 30%. So it's not quite as effective as shielding. And then you have the concept of spacing between them. So how close are those logs together to when they act as one? So just to give you an idea of how this works out, we went through for different spacing ratios for 4 of these documents, Design Guide 10, the New Zealand Standard, Cranes and Derricks, and FAM, and looked at a standard 10-member bay at different spacing ratios and depths. And what you'll see on the right under total, that is sort of the effective number of beams for wind load. So we started with 10 beams, and what we come out with on the right is how many beams are actually acting fully for catching the wind. And for a wide flange condition, we're generally more in the range of a spacing ratio of 5 to 10, right? You have an 18-inch beam with 10-foot spacing, something like that. And so ASC Design Guide 10 works out to be the best in most of those situations, right? You have an effective beam of 2 to 5, something like that. This is in comparison to ASC 37, where out of the 10 beams, you have an effective ratio of almost 9. So you just cut your wind loading by a significant margin, at least in half. For joists, something similar occurs, except in this case, you're more around 2 to 5 for the spacing ratio, and FEM 1001 is a little better off than Design Guide 10 for these cases. So there's a bunch of different tools that you can look at and compare to see what you can get your best numbers from. Also deck. Deck helps. A little, right? Not a lot. So you would think that once you put the deck on, it's great, but the wind still gets up under there, and there's really not a lot of research in this department. I think it's a place where we can get a little more out of it, and we just haven't done it yet. The actual reduction is documented in wind loads for petrochemical facilities. So it's this equation here, 1 minus 0.2 times A of floor beam divided by A sub S. And what that works out to be is absolute maximum reduction of 20%. Like if the only thing you have is floor beams. In practice, it's really more like 10%. So a lot of times I have an erector say, well, the deck is on, so there's no more load, and he's not right. Site-specific velocity reductions is another potential. So do you really need a hurricane plan? That is a very good question, because there is a direct conflict between AISC's Code of Standard Practice and ASCE 37. So AISC's Code of Standard Practice, underlined in red, says the erector need not consider loading during erection, blah, 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 from such loads as hurricane, tornado, earthquake, explosion, or collision. So it flat out says you don't need to consider it. But it also flat out says, except as specifically identified by the owner's designated representative, who can just as easily say you need to meet the standard of care provided by ASCE 37. So this is an issue where the day you get the job, you need to discuss with the general contractor and the owner what the expectations are regarding hurricane planning, right? Because it is a gray area in the code right now. Also, remember the ASCE 37 is not mandated by law. It's not referenced as a requirement. So you can explore the creation of job-specific criteria for evacuation policies and acceptable damage. I go through some numbers here, but basically the ASCE 37 reductions are based on the assumption that the risk in a 50-year period of the permanent building should be matched by the risk of your temporary construction condition, which is about a 7% probability of exceedance, that the storm you're designing for is going to be exceeded. So if the owner is okay with the 10% probability of exceedance, then you get to reduce your forces, so on and so forth. So it's a conversation that can be had at the beginning of a project. Second, it's sort of helpful to understand where the ASCE 37 reductions came from in the first place, because they really are not based on locality, right? There's not a map, there's just a single reduction. And they're fairly dated. A lot of this information came from Rosowski's paper in 1995, and he looked at wind load data through, I think, 1979. So we're missing 40 years of wind load data. That is built into more recent ASCE standards. And if you look at what was done, he looked at wind load monitoring stations all over the country, and he looked at sort of the worst case reductions. So the minimum reductions over the whole country are shown in red, right? 0.82, 0.86, 0.9, and that looks really familiar to what actually ended up in the code, right? They smoothed it a little bit, 0.8, 0.85, 0.9. But if you look at just the median numbers in that same paper, that 0.8 is 0.68. That 0.85 is 0.73. That 0.9 is 0.8. So there's a lot of reduction capability that can be had by looking at locality. So the only real good way to do this at this point is to scour wind records and come up with a reasonable reduction. And generally we do that by hiring a wind tunnel consultant. So most wind tunnel consultants will perform a desktop wind tunnel study for reductions in wind speed for locality and construction duration. This is not expensive, and for any reasonable size complex project is worth its weight in gold. They will produce a table, something like this, where they have your construction period and a time frame, and here's the velocity you should use. Right? Saves a lot of heartache. This is a recent job, and if you look at this, the force reduction is sort of the key here. For less than 6 weeks, we have a reduced force of almost 43%, cut it almost in half. Right? That has a huge impact on the design of bracing. Even for longer periods, we're up 20% reduction. So that's one possibility. The other possibility is to sharpen your pencil, right? Engineers can do engineering stuff and spend more time with analysis. So, you're talking about things like staging in the stiffness of the deck and then the stiffness of the concrete, looking at partial restraint of supposedly simple connections, base conditions. All these things can be done. All these things take time. Time takes money. So it's a sort of give and take with how much time and fee is available for you to be able to do these sort of things and the bracing that comes out of them. One thing that helps a lot is early involvement, design assist work. If the erection engineer and the erector can get on board early enough to affect the permanent design in a positive direction, a lot of the costs associated with temporary bracing can be eliminated or reduced. So that's now. Let's take a look towards the future. What can we do? Well, one of the things we're looking at doing is producing site-specific maps in future editions of ASE 37. So just like ASE 716, you'll be able to open up ASE 37 and say, I'm in Texas, I got 6 weeks, and here's my force, right? So that is your velocity. So that's sort of what we're doing right now with the wind tunnel study, except it's been done for you. That is in the beginning stages of moving forward. It probably won't even be in the next edition of ASE 37. You're looking at 2 editions from now. Industry-funded research on construction stage winds and shielding. It's something we're looking at doing. FDOT and some other companies have been looking at this for bridge design in terms of, stacking girders together and seeing what they have for different values of wind reduction and shielding. You can also potentially look into the adoption of material-specific guidelines. Masonry did this, and they basically said, yeah, our stuff's just going to fall over. And so they gave a restricted zone where if you go above 30 miles an hour, you have to stand the distance of the height of the wall away so that you won't be squished. This is an interesting concept for steel buildings. I'm not sure it'll fly, but just throwing it out there. Anchor rods. Anchor rods are always a problem. So most of the time, you're going to be using some sort of a cable brace on a low-rise building. And when you pull on a cable brace, it does 2 things. It pulls up and it pulls sideways. Before you have the benefit of grout, or in some case, concrete encasement of the base of the column, you pull the anchor rods over and bend them and potentially rupture them. So you need to check that, and you will find that it doesn't work a lot. You need to pay attention to the correct lever arm for when you're pulling on it. So Design Guide 1 uses a lever arm of 0.5 times the thickness of the plate plus the washer over 2 for the bending, right? It's only bending within that oversized hole of the base plate. But if you have shim packs and no grout, you end up with a lever arm that's that tall, right? It's a lot taller, and you're trying to bend these anchor rods, and they will bend nicely. The use of leveling nuts is somewhat helpful. So if you're using leveling nuts up onto the bottom, you end up with 2 lever arms. You have a lever arm up top, very similar to the final condition, and then you have a second one down below that you have to check, right? So this works out a little bit better for anchorage. So what can we do, right? How can we solve this particular issue? Well, one of the ways is stop doing things like this, right? This is on one of my jobs. This is a 14 by 300 and something with an HSS 14 brace, and it has 4 3/4-inch anchor rods. Stop that. You know who you are. Do something reasonable, right? So this worked in the final condition because the building was so heavy that friction worked, right? Works great in the final condition. It does not work great when you're setting the column and when you don't have all of that load on it. Right? It's not very costly to upsize an anchor rod in the design phase. The difference in cost between specifying a 3/4-inch grade 36 anchor and a 1 1/4-inch grade 55 anchor is minuscule. It's all in the labor, etc. You still have that. So if you look at a grade 36 rod, 3/4-inch, that has a shear of 6,800 pounds, right? If you upgraded that to 1 1/4 grade 55, it's almost 40 kips. So 6 times stronger for that little change. That's the very first thing we do on a lot of jobs. There's other ways to skin the cat. You can do things like putting angles on the side of it to have post-installed angles to take the shear. You can also just bypass the problem entirely, right? You can do things like this. This is one of our details where you put in an embedded cable loop or a piece of rebar or something like that, and so you don't take the shear through the anchor rods. You take the shear directly into the foundation. That works nicely, except for the concrete guys that forget the cable loop, don't want to put the cable loop in, hate the cable loop. So you just got to work out situational solutions for each of these particular issues. So one of the things that happens a lot for bracing is you don't have anything to brace to. So you come up with a dead man or something. And you need to be careful when you're looking at these because it's easy to lose some really important aspects. So let's take a look at a Jersey barrier, 3,600 pounds, and let's pull up on it at 50 degrees. What is the maximum load that you can put at the top of that column with a 1.5 safety factor? Right? You've got 3,600 pounds. How much P can you do before this thing falls over? Well, the problem is we're pulling sideways. And in order to resist pulling sideways, we have friction. But while we're pulling sideways, we're also pulling up. What does pulling up do to friction? It goes away, right? Hence the problem. So in this case, for your 3,600 pound Jersey barrier with a fairly normal friction coefficient, you only get a P of about 600 pounds. So a sixth of what your Jersey barrier weighs. So a lot of times I'll have a erector say, you know, the size of these is ridiculous for the load, and this is why. So for real world applications, this was the Indiana State Fair. This fell down in August 2011 under about a 60-mile-an-hour wind, and they were using guy wires to Jersey barrier lateral system. And if you look in that sort of stairwell, you'll see a Jersey barrier that was just dragged across the ground, right? Just yanked and slid across the ground until it fell in there. So this can and does happen, unfortunately. So how do we do that? How do we deal with it? Yes, sir.
Sorry to bother you. On one of the slides, real quick, you showed a 3/4 rod. Let's say you double the length of that anchor rod.
Mm-hmm.
Let's say it's 3/4 by 12 by 7/8 by 1 foot.
Okay.
For example.
Okay.
Does that do some of the same? Does that affect your length further into the concrete? Do you some more good or not? Or is it just the top part of the pole?
So the question is, does greater embed length affect the capacity of the anchor rods for lateral resistance? And the answer is a little, because mostly what we're failing is the bending strength of what's above the concrete. So as long as the tension strength is adequate to resist the tension component, then it's all in how big the diameter is. So one thing we can do here is increase drag. All right, you can bury your counterweight, so that takes away the sliding component. The other option is to increase weight, right? So you just get a bigger Jersey barrier, or in some cases, a bigger something. This is one of our details where we just buried a crane counterweight. There's generally some of those around. So we took that and we buried it and put bracing on top of it, which worked nicely. Another option is to utilize alternate supports such as helical anchors, which are fairly inexpensive and easy to put in. A final alternative is to use other foundations. So prior to the other columns going in, you can put a lug on the footing or anchor rods of another column and use that for temporary bracing. So one of the fun parts about erection engineering is there's no answer. There's no the answer. It's a solution waiting to be found. Okay, let's talk about connection design. So things like this happen a lot in the field. This is another one of our projects in which the holes were slightly misaligned, and I think that's weld on there, something. You got to pay a lot of attention to this. And connections for permanent buildings are not very good for the most part for temporary loading, right? So the connection forces on the drawings generally just consider the permanent condition, right? That makes sense. And most of the time for the permanent condition there is a diaphragm. And when we're building the building, there is not a diaphragm. So there are a lot of axial load paths and unbraced members that see things during the temporary condition that they may not see in the permanent condition. And the best way to deal with this is early. Don't call after the building is designed and when your crane is out there saying, what should I do for this truss? You need to get somebody involved early so that the erection forces can be fed to the connection designer, or if you're not delegating, they can be designed yourself, to be able to change connection types and loadings in a specific pattern to be able to handle these temporary forces. So just as you're laying out a job, you know, for axial load transfer, obviously the best is an end plate or a moment type connection. Double angles are pretty good. Single plates are great in tension, not as good in compression, but they're okay. Single angles are horrible, and seated connections have nothing, right? So that's sort of my order of yay to nay when you're first laying out a building as an engineer of record. In terms of beam, yes, sir.
Sorry,
The safety factor.
Do we need safety factor of 2?
You need the same safety factor as you need for a permanent building.
Why?
Because ASE 37 says so.
But we have engineering judgment, right?
Sir?
And what about engineering judgment?
Ah, engineering judgment, that wild animal that no one can find anymore. Yes, I am not going to stand here and say that I use less than the recommended safety factors for the design of temporary conditions.
Yeah, but designed for 100 years, and you have 1 month.
Yes.
Should be the difference.
Yes, his point is there should be a difference in safety factors for permanent design and temporary construction design. And there is. Generally, temporary structures are designed for an even higher safety factor for things like rigging to deal with the fact that they are busted around and reused job to job. For the design of the actual steel, it is up to the engineer in charge to make that decision, and that decision right now is to use the safety factors as required in the specification. For beam axial loads, beams in final conditions typically do not carry axial load unless they're called out as drag struts, but here we make them into drag struts. So if we look at, say, an 18 by 35 that's 35 foot long and has no deck on it, the maximum axial force you can put on that is about 20 kips, assuming that the connections are okay. If you put metal deck on it, that helps a lot, right? That doubles, more than doubles it. Maximum axial force now is 52,000 pounds. If you put a concrete slab on it so that it also resists constrained axis torsional buckling, now you're up to 250,000 pounds because you're buckling it in the strong axis, right? So for temporary conditions, it's much, much, much weaker. So how do we deal with that? Well, one possibility is instead of using a W18 by 35, if you get there soon enough, you could use a 16 by 36. It weighs 1 pound more per foot, and it's 50% better, right? Because it's a shape that resists column loads a little bit better. Another possibility is to temporarily brace it. Normally, you've got a lot of filler beams in a row, and if you brace each filler beam temporarily to one next to it, you can mobilize the axial capacity of those adjacent beams to help you as you're designing drag struts. And you can decide, at what wind speed perhaps you need to install these or require them to be staged at certain points. Let's talk about cable brace attachments. We've talked a little bit about cable bracing. This is an issue that comes up a lot. And cable bracing is generally lashed to, say, the bottom of a column, right? And the format and efficiency of that lashing depends on who did it, what mood they were in, what time of day it was. It's all over the map. There's really not a good answer to this. And the potential issue with it is if you choke it too tight, your forces get magnified. If you choke it too loose, there's a chance that it's going to run up the column, unless you do something like this, which is to put on a stop angle. If you have ever tried to tell an erector that they need to weld stop angles onto the bottom of every column on the job, you are in for a treat, because the answer is, are you crazy? But some of them have developed some potential solutions with using clamps and things like that to help resist vertical movement of the choke. What we decided to do is go out and test it. So we had a pilot test program occur at Virginia Tech with some industry partners, and I got an iron worker and went up to Virginia Tech and let him lash cable loops onto the bottom of a column, and we pulled on them. So the test setup looked like this. So at the bottom, we had a section of a column with different styles of cable attachment. Here, it was just a normal choke that he wrapped back. And then at the top, we had an actuator with a lug. And the cable itself was oversized. We were trying to force the failure to occur down at the connection to see when this would break or slip, etc. And so we varied the angle of the cable. We pulled up on it at 45 degrees, 50, 60, things like that. And more often than not, we ended up with this, where it stayed right where it started and we snapped the cable in half. However, at higher angles, we ended up with this. We had a stop angle on there to prevent it from rising, in infinitum, but it did slip. And this was a well-timed photograph that shows it in the middle of slip. So it does happen. Just for your viewing enjoyment, here's some of those tests. Slow motion. So that was the outer fibers breaking. The diameter of cables being tested range from a 1/2 inch up to 3/4 inch. And so you'll see they'll spin as they start to unwind the cables, and then the fibers will pop. And then a lot of the times we ran it up until the core also broke, because we like breaking things. We did manage to break a couple of the shackles and one of the turnbuckles too. So again, no slip. These were at fairly low angles, no slip. This one was at a fairly high angle. Slip. That's what we're trying to prevent. So the answer was, I can't tell you, because it was proprietary. Sorry. But we are creating a research need statement for AISC, Impact, and others to hopefully provide some industry-wide guidance, where we're looking at a much larger series of tests that, based on the information that we got from some of these proprietary tests, to look at different column types, different wrap types, things like that, with the hope of producing a industry guideline and design procedure for the bases of columns. This is still in review by AIC. It has not even been approved, but it's something that we're trying to move forward with, so that we can share this kind of information with the industry as a whole, with the hopes of making things a little more standardized. All right, let's talk about sequencing. So this is a pretend building, but it represents a lot of real buildings I see. And you'll notice that there's several bays that have no bracing, and then there's a bay that has bracing. So as an engineer, where do you think I want to start the erection? In the middle, right? We start where the bracing is and move out. As a general contractor, where do you want to start? From the end and move all the way. With my luck, guess what happens? They start there and they move inwards, right? This is exactly what happened on a major building that we designed, that we were the erection engineer on, just on a bigger case. So if you can get involved with the GC early enough to affect their sequencing, and you aren't the only party, right? Sometimes it makes a lot of sense to go from one end to the other in terms of efficiencies, but there are some times where maybe you could start a couple bays earlier and it would eliminate a lot of issues with the temporary bracing. And it's not that hard to identify that. You know, a couple hours with a set of drawings and you can sit down with the GC and say, it would really make some sense to go here, here, and here as you're laying out this sequencing. Right? The other thing to consider is how much can the erector put up in a day? Right? If he could erect this whole thing in a day, who cares where he started? Right? As long as it could handle the daily wind load during the erection. So you need to have an idea of what the erector can produce. And the only person who's going to tell you that is the erector. Right? But to give you an idea, I did an informal survey of 10 erectors across the country, California, New York, Texas, Florida, Vegas, just guys that we work with on a general basis, and asked them how many pieces on average can you set with one crew in an 8-hour day for low-rise, columns, beams, joist categories, and mid-rise, columns, girders, filler beams, truss assemblies. Of those 10 erectors, 6 responded. Of the 4 who didn't respond, 2 are in this room. Tisk, tisk. So here's the answer. Erector 1, 2, 3, 4, 5, and 6 with a bunch of numbers, and it really didn't bounce around too lot. There were highs and lows, and there's a lot of jockeying around that goes with this, right? So there are days where they're not going to do anything because they just got 8 loads of steel and they need to shake it out. There's stuff like that, and we tried to sort of average that into these numbers. And as a median, reasonable numbers for a low-rise building, you're looking at 30-ish, 35-ish columns and main beam lines, joists about 40. For a mid-rise building, columns, main girders 25, filler beams about 35, and sort of nebulous fabricated truss assemblies, depending on how big they are, you're going to be able to put up a couple, right, 4 or 5. So there were some other interesting notes that came out of this. Everyone assumed that they were using a conventional crawler crane as sort of the basis. If you're using a hydro, that reduces the counts by anywhere from 5 to 20%, depending on the erector. Tower cranes, most people said it was a wash from the crawler. A couple said it was actually somewhat faster, depending on if you had a good operator or not. High-profile jobs result in lower piece counts. That's a loaded statement, but it's true. Misfabs reduce piece counts, obviously. And, a lot of the guys I were talking with had a lot of years in the industry, and they said that piece counts have gone down and down and down as safety has gone up and up and up. So that's not necessarily a bad thing. You have tie-offs, you have safety meetings, you have erection engineering. So a lot of that has produced slightly lower piece counts than you might have seen in years past. But again, they weren't complaining, they were just stating. So lateral system issues. So if you look at the permanent system for a lot of buildings, they use the diaphragm, right? So you might have an offset brace frame like this, where the whole front row, page toward us, has no bracing in it. Right? That works great in the final condition. It works not so much in the construction condition. So you end up having to put in temporary bracing. Again, generally cable bracing, but sometimes permanent bracing. Not permanent bracing, but hard bracing. So if you try to put cable bracing in any row in line with the permanent bracing, it's going to do nothing once the permanent bracing appears. So you've got to be cognizant of the difference in stiffnesses between your temporary bracing and the permanent bracing if you're trying to combine systems. You also got to watch out for fully welded moment frames, right? These are great after they're welded. So in the temporary condition prior to they're welded, that is no different than any other simple shear tab. It's something you need to consider in your sequencing. So some possibilities are to, again, recognize these are not effective until they're complete. You can ask the EOR for design moments, and you can design a temporary moment connection yourself if you really need it. There are alternates that could work better. Bolted connections work great for immediate moment capacity. There's some proprietary solutions, such as the side plate bolted designs, things like that. Anything that you can get up and in place quickly. Okay, so we've got 15 minutes left. We're going to go through what I would consider to be the pieces of an engineered erection plan and how to minimize some of these impacts. So, parts of an erection bracing plan. First part, erection connection forces. So this is one of the very first things we do on a job is we perform a staged analysis of the job to see if there might be locations where our construction loading is going to exceed or be in a different sense than the permanent. And we will provide that to the connection designer in just a PDF markup. Hey, 300 kips isn't good here, please provide 350. Please change this member force. Please add some minor axis moment capacity. That's all great if you do it before the connection designer has designed the connections. If you don't, then they have to go back and redesign them, which costs money. If you wait until they're already detailed and fabricated, then it gets even more fun. So the key here is early involvement. Revisions to the permanent structure are given sort of in the same time frame, generally in our standpoint, a PDF markup, where we'll go in and say, please change this member size, please add this here, and then it becomes a discussion with the engineer of record, right? Because hopefully you have an EOR that is willing to work with you. Most of the ones that we work with are, and to be able to produce a more constructible and erectable building. Your plan then needs to have the location and detailing of all temporary bracing and shoring. So we generally put out color-coded plans sort of like this, where we have temporary bracing highlighted in an orange or red color. In this case, this was a hurricane plan, so the red you had to put in and the orange you were putting in during a hurricane. And this was also a shore job, so we had details like this where you have a shoring tower and jacking systems to relieve the load after the truss was in place. And all that is incumbent upon the erection engineer to design and provide. And then we provide sequencing drawings and steps. So basically a Lego set, right? This is an image right from one of our drawings where you say, you know, put this up, step 1, 2, 3, 4, 5. It's really an elaborate set of Lego plans that's intended for the guys in the field to be able to look and see, you know, here's what I'm doing today, and here's how I do it. So step 1, step 2, you know, here's where I'm putting bracing, here's what the bracing looks like, that kind of stuff. And then if you're hired to do it, your plans also need to review crane planning activities, critical lifts, logistics. There's a lot involved with the construction site. And so your role can grow way beyond what would be considered typical structural engineering. And again, a lot of this involves heavy coordination with the general contractor, fabricator, erector. And that will be a seminar for another day. So, how to minimize and plan for impacts. Mitigating impact. Establish erection engineering requirements, expectations up front in the bidding stage. If you're carrying a lot of money for erection engineering and nobody else is, guess what? You just lost the job. Maybe. It depends on how low you are. But it'd be a good idea to let whoever is creating the bid package, you know, assign the fact that there needs to be an engineer direction plan, if there indeed does need to be one. Incorporate the erection engineer, if required, early to be able to engage with the engineer of record, right? If you get in there early enough, you can affect some of the design in the permanent stage prior to it being even issued for construction. You can help guide the erection sequencing, like what we were just talking about, where perhaps we could start at point A, then point B, and save a lot of time and a lot of money. You can begin developing loading requirements as early as possible, early. And then include in your bid allowances for larger jobs, monies for a construction wind study. This is what I was talking about earlier. These are, again, not expensive, and they provide a tremendous return on their value in terms of construction bracing, right? If you get a 30 or 40% reduction in your wind loading, that translates directly to saved money in connection design, in bracing, in foundations for temporary towers, things like that. Have some additional money in there for connection design load cases, right? If your connection designer is unaware that he's going to be being fed a whole different set of forces, he's not going to have that in his fee, and he's going to charge you for it. Additional temporary brace detailing and fabrication, need to think about that. A conversation ahead of time if something needs to be held, especially if it's more than just cable bracing, if it's some sort of a hard brace, then that needs to be included. And anything you might think would be necessary for a base building modification. And sometimes that's not additional cost. Sometimes base building modifications can result in reduced cost because you can change the building design in order to make it more efficient to erect certain pieces of the structure. So with that, we actually have a couple minutes left, which is good. So we'll open it up for questions. Thank you. Yes, sir.
Who should be the definer of when temporary bracing can come out?
The erection engineer. The answer, or the question is, who should be the definer of when the erection engineer, or when the temporary bracing can come out? That should be specified in the engineered erection plan.
Well, what if the general contractor says, well, we're going to start making pours of concrete, for example, on XYZ slab, and your bracing, your temporary bracing has to come out to accommodate that request. So is that still force that semi-responsibility on the GC, or does it still force that on the engineered bracing designer?
So the question is, what about when the GC wants to make a pour and your bracing is in his way? Whose responsibility is that? The answer is that needs to be coordinated by the erection engineer during the planning process, right? So you need to work with the GC, and you need to analyze that state of the building with those braces not there, with whatever is there. And if it doesn't work, then the responsibility becomes the general contractors for not following the plan. Yes, sir.
Are there any inspection requirements?
Good question. The question is, are there any inspection requirements for any of this? That is another gray area in the code. ASC 37 does not speak to inspection requirements. Our firm's typical process is for us to have someone go out there and look at it ourselves at key times during the erection process. This is one of the parts of the industry where the concept of job observations and don't go there because it's means and methods doesn't apply, because you are the means and methods. And so the more you can get to the job site, the better. Yes, in the back.
Shielding, do you guys ever look at the EIX convergence method?
All right, the question is, with shielding, do you guys ever blah, 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 blah? No. Is that a good method?
Well, it's something in the power industry that they use all the time for platforms, but shielding.
There are so many different shielding documents. I listed about 10. I've got another 30 somewhere else. I probably have looked at that one. I have not yet found the golden bullet. Okay, so what you saw when I did a comparison of 4 or 5 of them, that's about how it shakes out. In some cases, document A is better. In other cases, document B is better. There's no, yes, this is it. We are working with a couple of the wind tunnel companies right now to develop some testing to try to basically parameterize this. Same thing that New Zealand did to come up with their code, but just so we can see what was done for different beam spacings and depths. And hopefully that'll turn into a research paper that can guide some future American provisions. Yes?
The wind loading and construction time, what's included? Only the erection time or slab pulling?
Yeah, the wind loading erection time, the duration, is the question. What does that include? ASC 37 is pretty clear that that includes until the building cladding is up. That is not necessarily what everyone does in practice, but that is what ASC 37 says, is that it's from the time the first column goes up until the building is clad, thus becoming the permanent condition. Obviously, the state of the structure is changing during that whole time, so you have more resistance as the diaphragm is completed and things of that nature. So the Code of Standard Practice does not require you to take into account loading from stuff other than structural steel and the items directly associated with structural steel. So, for instance, if someone's putting up cladding before the building is completed, you're not required by the Code of Standard Practice to consider that in your wind loading up front. Now, you'll need to talk to the GC, because the fact of the matter is it's going to happen. And so in an effective plan, that needs to be considered. Yes, sir, in the back.
Are there situations where you're brought on board to be the erection engineer when there's an EOR on the job? So someone else has designed it, and you've been brought in just to address those issues.
Okay, so the question is, are there situations where the engineer of record has designed the job and we are brought in just as the erection engineer? The answer is that is what happens most of the time.
What's the interaction between the who? Is the EOR still ultimately responsible for the design?
The engineer of record is, so the question is, who is ultimately responsible for design? The engineer of record is ultimately responsible for the design of the structure in its complete state. The erection engineer is responsible for the design of the structure in every stage until it gets to that complete state. In situations where we change aspects of the permanent building design, you are co-responsible in that we will say, can we have this beam upsized to an 18 by 35, and the ERR will review it as it pertains to their permanent loading and approve or disapprove. Yes, sir, up front.
The engineering community in New York City is contemplating a pretty important code change requiring the erector to submit an erection plan prepared by a licensed engineer hired by the erector, not just for temporary shoring and bracing, but let's say there is not the case, but in all instances, a plan prepared by a licensed engineer. Is that unusual in your experience in most jurisdictions?
So the question is, a jurisdiction in my state is thinking about requiring basically a engineered erection plan to be submitted by the erector for all structures. No, that's not normal in my experience. We see it in government buildings, so it's required in Army Corps buildings and things like that as a matter of no matter what. There's a couple of outs, but generally they require an erection engineering plan. I would be in favor of that to a point. So it would be more like sort of the Structural Engineering Act, where buildings over a certain height or of a certain complexity, it would be required. That, I think, is a good idea. To require it for everything, I don't think everything needs it. Yes, sir, this will be our last question.
When you're talking about the cables and you're testing them out for slip, is there test data for values on those cables available?
The question is, when we were testing the cables, is there test data available? Not publicly. That was a privately funded test, and so that information is shared only with the sponsors of that particular testing. But that test, again, was a pilot for what's hopefully going to be a larger set of tests that will be available. All right. Thanks so much for your time. I appreciate it.